Okay, well, let's continue. Let's looking at the integrals involving the arcsine or arctangent. They involve these expressions. And when we look at number 4 here, which of these two then are we focusing on? Again, we're down here, right? It's not, I don't see the square root symbol for one thing. What's different about it now? This time the x squared, last time we didn't have the x squared, but now we have the x squared. And here we're supposed to have a 1, but here we have a 4. And so what I need here is a 1. The number 1 here. Right, so how can I get a 1 there? I mean, I just can't, I can't subtract 3 from the denominator. That totally changes the problem. So what can I do? Well, here's what we can do. We can indeed factor out 4 from the denominator. And you say, wait a minute. I see that I can factor a 4 from 4, but the coefficient of x squared is 1. There's no multiple of 4 there. How in the world do you factor out 4 from just 1x squared? And the answer is easy. Can you factor a 4 out of 1? Yes, you can. 4 times what equals 1? 4 times what equals 1? Answer that question. 4 times what equals 1? Answer, 1/4. Right? This is 1/4 x squared plus 1 when I factor the 4 out. Multiply back through by 4. What do you get? 4 times 1/4 is 1x squared. 4 times 1 is 4. I can factor out a 4. I can do it. I can factor out a 4. And so we now have the 1 here. This 4 can come outside the integral. Now be careful. Does it come out as 4? It's 1/4, right? It comes out as 1/4, not as 4. It's not up here. If it was up here, 4 would come out, right? It's 1/4. This is 1/4 times this, right? So let's do that. And I want to rewrite this 1/4 x squared a little bit differently. This is really x squared divided by 4. X squared divided by 4. And what is x squared divided by 4? Well, I can write that as x divided by 2 quantity squared. Right? It's x squared divided by 4, which is x over 2 quantity squared, right? X squared plus 2 squared, or x squared divided by 2 squared, x squared divided by 4, right? And this now helps me to see that I am now essentially almost in this form. Instead of x squared plus 1, I have x over 2 plus 1. Well, that's, you say, well, that's close enough. No, it's not. It's got to be exact. So what I have to do here is my substitution must be let u be x over 2, which again is 1/2 of x. Keep that in mind. So what is my du? What's the derivative of 1/2 x? Derivative of 1/2 x is just 1/2. So du is 1/2 dx. All right, but I have just 1 dx up here, so I'm going to multiply both sides by 2. I get 2 du equals dx. And with that transformation, my integral becomes what? I've got this 1/4. Don't forget the 1/4 integral. What's my dx? My dx is 2 du. I'm just going to write that up there. And then I have x over 2, which is u squared plus 1. Pull this 2 out, right? And the 2 comes out as 2/4. This is 1/2 the integral of du over u squared plus 1. Do you see what I've done? I've transformed this by the substitution and a little bit of factoring to help get that 1 there exactly into the integral form I need. Now it's exactly that form. You know, it's not x, but it's u, but same thing, right? So it's going to be tangent inverse of u, right? Tangent inverse of u. So that's my answer, 1/2 tangent inverse of u plus a constant. And then don't forget, I'll go back to the original variable. U is x over 2. And so I get 1/2 tangent inverse u is x over 2 plus c. There is the antiderivative. Wasn't that fun? Wasn't that exciting? Got to factor a 4 out of 1. Didn't think you could do it, but we actually could. Did this nice little substitution. Get that 2 pulled out, and then we're there. We've got the form that we're looking for. Okay. Well, if you think about it, looking at where this 2 came from, right? It was indeed, when we factor out a 4, we had 1/4, so it was 2 squared there was 4. So if this 4 could be thought of as being 2 squared, and in general, if this is any number squared, say 3 squared 9, or 4 squared 16, or 5 squared 25, or even square root of 7 squared, which would be 7, x squared plus 7, right? Then it turns out that we can go through the same process, and what we observe is, in general, if a is greater than 0, the integral of dx over x squared plus a squared is 1 over a tangent inverse x over a. And you could redo this whole problem with a as a constant, and you can see it would come out, because you would have, instead of 4 here, you'd have a, and this again, sorry, instead of 4 you'd have a squared, and instead of 2 you'd have a, and work it all the way down, and you're going to get 1 over a tangent inverse x over a, right? A here would be 2. Okay, and so this is a general form that you can use. In fact, there's many integral forms that we'll talk more about. A lot of them we'll know, and we should know, but some of them we will later on use a table to look up and find. But that's the idea behind this one. Okay, so let's take a look at another one. Now, which of the two is this one? You say, well, it's definitely not that one. Doesn't have the radical. Okay. We've got problems, right? I got the x squared. That's good. But then instead of plus 1, I've got plus 26. And then I also have an x term. There's no x term here. Oh, man. Is this then not a inverse tangent integral? Well, it actually is. It is. But to get you to see that, we have to recall something that we say is completing the square. Do you remember how to complete the square? You remember how to complete the square? The idea there is, right, if you have, say, x squared plus 4x, how can I complete the square on this? How can I complete the square? What do I mean by complete the square? I want to be able to write this as, x plus something, in this case, squared. Okay, so what would I need to add to this to make it a perfect square? Well, it turns out you take what? This coefficient here of the x term, which is 4, divide it by 2 and square it. So, of course, that's going to be adding 4. That's what I need to make this a perfect square. And then this factors then as x plus 2 quantity squared. And the reason is, we see that because when I look at x plus a quantity squared, this is, remember, x squared plus 2 ax plus a squared. And you can see, if I take the coefficient of x, which is 2a, divide it by 2 gives me a, square it, that's what I need to add to make it a perfect square. Now, if it's x minus a quantity squared, it's going to be x squared minus 2ax plus a squared. But the same thing happens. If I take half of negative 2a, I get negative a. Negative a squared is, again, positive a squared. So you can see the difference there. So when I look at this particular one here, what do I need to complete the square? I've got x squared minus 10x And I'm going to leave a little space here and put the plus 26 here. Okay, so we do have to make a little adjustment here. So first of all, what do I need to complete the square? I need 1/2 of the coefficient -10 all squared. Half of -10 is -5. -5 squared is +25. Okay, so I'm going to add 25, but some of you should say, wait a minute, you just can't add 25 to the denominator. If I add 25 to the denominator, you're totally changing the problem. And you're right, I can't do that. So I'm going to fix it. When I add 25, I'm going to immediately subtract 25. There we go. 25 minus 25 is how much? It is 0. You say, well, that's dumb. You haven't changed anything. Well, that's true. I haven't changed anything in terms of the total value of this expression. It's still x squared minus 10x plus 26. However, I have changed something, because what I'm going to do is I'm going to group, right, regroup. I'm going to group these together. That's a perfect square I can factor. And what do I have left over? -25 plus 26 gives me my +1. Hey, that sounds good. All right, so this becomes x what? Since I have minus 10x, right, it's going to be x minus, and what was a? That was half of 10, which is 5. Quantity squared. That's going to give me the x squared minus 10x plus 25, and then the -25 plus 26 is 1, and that's going to go outside here, +1. So go ahead and FOIL x minus 5 and add 1. What do you get? X squared minus 10x plus 26. This is the same thing, but this now is in the form we need it by completing the square. And you have to do this little, add and subtract thing to keep things balanced, so to speak, or the same expression. So this is now x minus 5 quantity squared plus 1. Okay. Now, does it look more like, obviously, our tangent inverse integral now? Almost. Little slight manipulation. What do we have to choose our u to be to make this to work? I've got my 1 here. I need the u to be the x minus 5. So I'll get u squared here plus 1. So we do have to find our du, but this time what's du? What's the derivative of x minus 5? It's just 1. Du over dx is 1, so du is equal to dx. Right? And so our integral becomes, the integral dx is the same as du of u squared plus 1, which is the inverse tangent of u plus c. And then again, I go back to u, which is x minus 5. And so I have tangent inverse x minus 5 plus c. Okay. Let's take a look at one more here. Now, which one is this going to be like? Is this going to be the one that evaluates as the inverse tangent, as we've been doing a lot of, or the one that evaluates as the arc sine? I think we're going to go with the arc sine, right? We see the square root, okay? But we have, again, problems, right? So what do we need here, first of all? I don't need a 9 there. What do I need? I need a 1. How am I going to get the 1 there? Do you remember how we got the, in the last video, how we got the 4 there? We did what? We factored out, right? So I'm going to factor out 9, and it's going to be a little tricky here. So I'm going to factor out 9. I've got the 5 dx, and under the radical, I'm going to factor out the 9. So what's that going to leave? Factoring a 9 from 9 leaves 1. Can you factor a 9 from a 16? You say there's no way. We factored a 4 out of 1. I see you could do that. Now 4 times 1/4 is 1. But you can't factor a 9 out of 16. Well, you can. What happens when I factor 9 out of 16? What am I left with? Answer, 16 ninths. 16 ninths is what you're left with. all under the radical though. All right, what's 9 times 16 ninths? What's 9 times 16 ninths? 16, right? If I distribute this 9 back through, I get right back to this thing. But that's what I need to get the 1 there. Okay. Now, again, I want to think of this as being a perfect squared. So what is this squared? What's being squared here? What's being squared? Well, what's being squared to get 16? 4. What's being squared to get 9? 3. What's squared to get x squared? X. So it's 4/3 x quantity squared. And so let's clean this up a little bit. Another thing I'm going to do is I've got the square root of 9 times all this in parentheses. Well, the square root of a times the square root of b, or the square root of a times b, is the square root of a times the square root of b. So in other words, I can write this as the square root of 9 times the square root of 1 minus, and I'll write this as 4/3 x quantity squared. All right. So in other words, I can break that up, because again, it's the product to power rule there, because really square root of x is to the 1/2 power. So I can distribute the power over a product. Of course, the square root of 9 is how much? That's just 3. Okay. Now, what substitution do I need to make? Again, look at what I'm trying to get to. 1 minus the variable squared. 1 minus the variable squared. What's my u going to be here? My u is going to be 4/3 x. Therefore, my du is just 4/3 dx. Okay. And I'm just going to do this time. I'm just going to solve for dx here and replace it here. Usually I try and get things to balance, but I'm just going to do it another way here. Multiply both sides by 3/4. I get 3/4 du is equal to dx. Okay. So I'm just going to leave it that way. And so what does my integral become? What do I have? Up top, I've got the 5 times the dx. What's the dx? That's 3/4 du. And then down below I've got the 3, and I've got the square root of 1 minus u squared. Okay, 1 minus u squared. And I can clean all this up here. Notice up top here, 5 times the 3/4, that is going to be 15/4, right? 15/4. And I'm dividing 15/4 by 3, and that's all a constant, so I can pull that out. So in other words, I'm going to get 15/4 divided by 3, and what's left? I've got the du up top and the square root of 1 minus u squared. So again, constant multiples I can pull out. I can't pull out anything involving u under a variable, but I can pull out the 3. Notice it's in the bottom. 5 times 3/4, 15/4 on top. Now what is 15/4 divided by 3? Of course, that's 15/4 times 1/3, and 3 goes into 15 5 times, and so I get 5/4. So this is equal to 5/4. Okay, but I know the answer now, right? Because what is this integral right here? Integral of 1 over the square root of 1 minus u squared. Well, it's the same here. With x, it's going to be arc sine of x, or inverse sine of x. I'll use the arc sine this time. So it's arc sine of u, right? 5/4 is what this number came out to be. Arc sine of u plus c. And now what? I need to go back to the original variable. What was the original variable? U was 4/3 x. Whew, that was a lot of fun. Pretty exciting. All right, lots of little steps in the process, but that's what you have to do. You're going to attack more and more challenging integrals You've got to use substitution and these factoring techniques and so on to get the integral, rewrite it, simplify it, into a form that you recognize, right? Once we get it into a form we recognize, we're good to go. So being able to factor out to get that one there, we needed the one there, and then recognizing what we have to choose for our u substitution here. And don't forget the du. It is important. This little 3/4 factor is important. If you don't have that factor involved in the process, then you're going to be off by a little bit. You can always check again by taking the derivative of this and make sure it gets back to what you started with. Okay, we'll stop here and we will do some more in the next video.